to keep that cabbage rolling.
Did you post on the Discord, or do you want me to post it?
I already posted.
Oh, you posted, yeah. That's
Okay,
it. Okay, cool. So let me load up. You can look at my phone for.
Oh, I was just going to load mine up.
Oh,
I
it
got
doesn't
mine.
matter to
Yeah,
me.
that's fine. You hang on to yours in case you want to interact with somebody.
Oh, are you
Oh,
streaming?
look, I'm getting an ad for Anusol. Hemorrhoid cream. I got a comment on that. You can't let an opportunity like that pass you by. You can tell by the way I walk.
Oh, do you want to mute that?
Oh, damn it. Oh, hey, we're already on. Okay. Oh, I'm dancing. Oh, man. Welcome, welcome to another edition of the Tutor Wizard. I'm Tim, the T in TL and E now. We got Lorenzo
I'm the L.
and the L, and we got Ethan.
I'm the
Ethan's gonna. I don't want to torture Ethan. Ethan's a good guy. I don't want to drag him up here and make him do math, okay? But Ethan is focusing on how can we improve the stream because he's got that kind of brain that says, marketing, but don't tell us, Mom. So if you hear me talking, this could be mostly me today, but I'll be talking to these characters off screen. And I may be dragging, what's your name again? Lorenzo. Sorry, I had a rough night last night, quite tired today. So I'm not promising miracles, but miracles may happen. Now, I do have to make a comment. I really, really, really have to make a comment. And the first comment is, how did my camera get turned? Can you help me with everything just rotated there. Yeah, that's kind of weird. There we go. We're trying a new way to hold the camera up here too, because we're just poor Twitchers. Is that a social class? I wonder. There's middle class, lower class, and then there's the Twitch.
We're Twitchers. Yeah, we are the poor Twitchers.
Excellent. Anyway, what I wanted to say was one of the ads that ran when I first started the Twitch stream was for, and I'm not mocking so much, I'm just pointing out that there's an ad for Anusol, which is just another way of saying hemorrhoids. And now I'm going, I know there's an algorithm that chooses these things, and I'm going, exactly how did we get associated with pain in somebody's ass?
I think it's personalized personally, but that's all right.
Well, it could be, because, it's notorious that I'm an old crab. No, I'm not really that crabby. I just play a old crab on TV. We were talking earlier before this whole thing started about, my point in time, I may have to take the Walter White approach to earning a living and to start cooking math. But we got to bring one of your drums for a rim shot.
Oh, there you go. Nice. Speaking of anusol.
Yeah. Well,
rim shots now? Okay, this is getting off the rails real quick.
Good one. Or we could have a theme song. This has been done to death. I know it's been done to death, but we could have, we can't do any of the copyright versions of, so there's another camera going on over here too, so I'm going to interact with this camera momentarily.
Yeah, you just keep doing what you're doing. Don't
Okay.
worry about what I'm doing. Yeah?
We could probably, I don't think Ring of Fire is in the public domain just yet, because Johnny Cash just passed. I'd have to look up and see when that thing goes into the public domain, but hey, Ring of Fire. And rings are part of math. Ring theory.
We'll get to that, yeah. It's
Okay.
a list of things to do.
Okay, the math
There's
is everywhere. It
brain
permeates,
Adrian
mathematics permeates everything. And I know you're probably saying, would you just shut up and get on with the day? And I might not. Haven't made up my mind yet. So what we see here today, this is TL and E Talk Stats, episode number 5. It's Red Chalk Day because I found some juicy red chalk, but I'm just wondering, it doesn't really show up that well. So you know what? I'm probably going to use the blue chalk for the math, but no judgments on the red because, it's all good. It's all good. Now, what are we going to do today? Well, I know yesterday on our previous stream that Lorenzo was talking about degrees of freedom. And I'm going to kind of explain degrees of freedom as I do to my first year students in statistics. See what you think about my approach to explaining this. There's a couple of different ways to do it. I take a fairly straightforward method, one that's easy to understand intuitively. So I'm going to do that first. That'll take about 5 or 10 minutes at the most. And then we're going to talk about one-way analysis of variance. And what I'm going to do today, and I haven't prepped any of the numbers, by the way. Well, I did bring a calculator, I think. No, maybe not. You know, I may have to wing it a little bit on that. We'll see what happens. Winging it is fine. But I'm going to compute the sum of squares manually. I know current practice is to use software for computing sum of squares and computing the whole analysis of variance thing. And that's fine. Probably end up, I'm going to do some demonstration computations, and then I might make up more user-friendly numbers. I haven't really made up my mind because whatever we do on this stream is very much ad lib. And I think winging it is our way of doing things, and winging it ties right into turtle shells. I got to remind me to do this with turtle shells, right?
Right.
Okay. We can
Or there was the other idea with the piranha plants, because Bowser,
yeah.
he's sick of Mario shit.
Oh.
So he was going to breed more piranha.
Come over here. The microphone's here.
I guess I've roped myself in now. So
Yeah,
yes,
explain the Bowser thing.
with an analysis of variance, what's going on is Bowser, he's sick of Mario shit. He really is. Barging into his kids' homes and beating them up all the time.
Stealing the princess.
Exactly. You know, after Bowser stole the princess fair and square, then Mario's got to go and steal her back.
Well, you know, possession is 9/10 of the law.
Of course. So what Bowser's doing is he's trying to breed more powerful piranha plants. So thicker stem.
Right. You were
and
talking about piranha plants yesterday, and
so
it
he's
went
trying to get
whoosh
them
over my head.
beefier, right? So he's trying these new treatments
Yeah.
on these piranha plants to try to get them to be
Mm-hmm.
bigger and stronger. So that's how we'll set up the treatment thing.
Okay, remind me to do that because I may end up missing out on that. But you know, we got an ad running. That's okay. But I did want to say, after this ad runs, this is. But then I'll probably forget what I'm talking about. So
Might as well start saying it.
oh, look, it's Anusol again, and they got a peach. You did that. Well, you can't put Anusol ads along with a graphical peach and not expect a guy to pick it up and run with it. Oh, it's hard, man. It's hard.
So what were you saying before you forget?
I don't even know anymore. It was something about
The Bowser? The piranha
and
plant?
and
The
oh,
treatment?
I know what it was.
Okay.
Oh, we're back. Okay, cool. What I was going to say was yesterday you were talking about, and with our online, I think it was e to the 2 pi I, and what's his face?
Sensation
from-
Black?
Yes, right. About how generations have changed. So current generation, everybody plays on Twitch, or Switch, whatever.
Switch on the Twitch?
The thing is, and then the earlier generation, the one you're in, you have the console. But I had to plug quarters in at the arcade.
Ah, yes.
You know, so there's actually 3 generations. There's plug-in quarters, then there's the NES, and then there's modern, current. So yeah, that's where we're at right now. Hey, and we've got.
Vanished edits.
Oh, hey, welcome.
Was that
No one here? Well, you are now. Welcome. So if you're just tuning in, we're going to do some analysis of variance today. We're going to do some chaos, some chaotic behaviors involving things and stuff. Lorenzo's mostly offline, off the screen today. We got another camera we're testing out here, so he's running with that. And we got Ethan in the background too. Oh, who else we got here today? Since I have to do both, I need my glasses too. Old age is a terrible thing. If you don't fear old age, you ain't old enough yet. I mean, I am famished. Famished edits. Excellent. Cool. So I'll probably be referring back and forth to this after getting up close and personal. Okay, so red chalk isn't going to work too well because I was just looking, it's not showing up that great. So let's get rid of this and get started. Whoosh. And since no one really wants to look at the back of my head, not even my wife actually, And that's not going to work very well now, is it? Crickets. I hear them.
I'm gonna get a recording of crickets and play them from now on.
Yes.
It's not crickets chirping, it's crickets clapping.
Well, you know how crickets make sounds, right? They rub their little
rub
legs
their legs
together.
together,
That ain't sexy. I don't know what is. Okay, we're gonna edging over there towards the ditch. So I was commenting driving in here today that one of the local radio stations is currently their playlist is going back into the 70s for some things, and it was Staying Alive by the Brothers Gibb, the Bee Gees. And if that doesn't highlight the 70s, I really don't know what does. Maybe KC and the Sunshine Band would be a little bit more recognizable, but not by much. Yeah. Okay, so if you were listening to Lorenzo's stream yesterday, he was talking about a little bit of chit-chat and explanation about degrees of freedom. So we're going to do first, and then we're going to segue into analysis of variance. That's my game plan at the moment. Just to recap, I'm going to take a fairly intuitive approach to understanding degrees of freedom. More mathematically sophisticated folk may say, well, you could do better than that. Just see what I'm going to do, see what you think. The whole idea is to give a basic understanding as to what degrees of freedom represent. And, say, it's a number of ways you can choose data and choose things to get a particular outcome. And that's the approach I'm going to take. So let's say we have 4 observations and their average is 80. And so if the average of something is 80 and there are 4 measurements, n is equal to 4, we can say that that 80 is equal to x sub 1, x sub 2, x sub 3, x sub 4 divided by 4, which is the definition of the mean, right? And that's all it is. Okay, well let's take and run with this and see what happens. So first thing, I want to get rid of the denominator. Let's cross multiply it. Yes, we could distribute the 4 underneath all the observations. It just gets clumsy. Let's not do that. So really what we have is 320 is equal to x1, x2, x3, and x4. Well, that means there's an infinite variety of numbers that you can choose, as long as they choose 4. What was that movie clip? Oh, Fifth Element. When the I can't remember the name of the
Bruce Willis?
well, no, they got Jean-Baptiste Emmanuel Zorg was paying for 4 crates of weapons for 4 stones.
Oh,
yeah. Not the Monda Shoe ones. They were the big duck people.
yeah, the gremlin-looking things.
Yeah.
Giant gremlin.
Well, anyway,
things.
he does some slapstick in there, quite literally. Anyway, I'll think of the name in a minute. Anyway, let's carry on here. So my point is that you have any 4 numbers, you get 320. The average is going to be 80. But let's say, for instance, that x1 is equal to 100. Okay, that's easy enough. So now we have 320 is equal to 100 plus x sub 2, x sub 3, and x sub 4. All right, so far nothing wrong with that. Let's move the 100 over here. So if I move this over here, this becomes 220. I'm just going to save some board space here. So what do we have? We have, as long as these 3 numbers, which there is an infinite variety, long as they add up to 220 along with our previously chosen number, we still get the same average. Well, we can repeat the process. So now, and it doesn't matter what order, let's do it this way. Let's let x sub 4 equal 150. Okay? Same thing. So now we have 220 is equal to x sub 2, x sub 3, and 150. Fair enough. Well, let's move the 150 to the other side because that's what we do in math, right? You like terms, variables on one side, constants on the other. Life goes on, sun keeps shining, Earth spins around it. Was it Galileo did that, or was it Tycho Brahe? The sun shines, Earth spins around it.
Oh, that was Copernicus.
Copernicus.
The heliocentric
Yeah.
model, yeah.
Yep. Try to make it funny, and then you have to check the peanut gallery for verification. Okay, so let's move the 150 over here. So
These
if we do
peanuts are
that-
food for thought.
Yep, so we get 70 is equal to x2 and x3. And again, we still have an infinite variety of numbers that we may choose from. As long as these two add up to 70, along with this and that, we're good. Okay, let's move over here. Now, we're going to let x sub 2 equal 40. Well, if I do that, I've got 70 is equal to 40 and x sub 3. And we move that over here, we find out that 30 is x sub 3. Now, here's the punchline to the joke. Remember, with degrees of freedom, we're talking about mean values. Degrees of freedom, for instance, in the t-test of the single sample mean is n minus 1. So this answers the question, why is it n minus 1? Well, we have 1, 2, 3 numbers that we are free to choose, and in a group of 4, if I choose those 3 numbers any way I want, when I'm done, the last one is fixed, it's chosen, it's determined by the previous 3, so hence we get degrees of freedom, n minus 1 is 3. I get to choose 3 of the 4 numbers. But once I do that, the last one is fixed by my choices. Degrees of freedom. And largely through the statistics that we talked about, it's the same idea. So what it come down to was, this is a statistic that estimates a parameter. So when we look at analysis of variance, there's a couple of different ways to compute degrees of freedom. It's always big N, or how many things, minus how many parameters you computed. So a little bit more sophisticated way, like in second semester statistics, they often tell you, okay, well, the degrees of freedom is how many observations minus the number of computed parameters. Well, this statistic is estimating the parameter mu, and there's one of them. There we go. Okay, so that's all I'm going to say about that. Remember, the idea behind a lot of this stuff is to simply get a toehold, a place to start understanding statistics. And the more you deal with this, the more it will become, I may say second nature, but it'll become more meaningful. Lorenzo, can you modify the camera a little bit? It seems to have wobbled over again, and I'm losing some of my
On it.
over here.
I don't know what's going on with that. Maybe
Yeah, I don't know. Something's a little wobbly. It's maybe, yeah, we'll make it work. There we go. There we go.
Over-adjusted.
Perfect. Ah!
The cord should be holding in.
There we go. Perfect. Perfect. I bet it is the cord, too. Okay. Enough of this nonsense. Let's carry on. I'm going to give you my farmer version of analysis of variance, and you're saying, wait a minute, farmers? Analysis of variance? What heresy is this? I grew up on a farm. I'm allowed to say that. So we're going to talk about data where we're interested in mean values. Which typically, if we're collecting samples, is t-tests. One sample has a formula, a confidence interval is a formula. Same thing for 2 samples. But what do you got? How do you do more than 2? Because the problem you run into when you start doing repeated pairwise comparisons is you start to incur a bit of an error. And the error grows the more comparisons you have. So oftentimes, one of the things they teach you is Bonferroni adjustment to the level of significance. We're not going to do that today, although it is a valid technique. And we will do it because I'm thinking September's coming up and we want to have second semester valid statistics here too. But what we're going to do is the analysis of variance, one-way ANOVA today. But we're not going to worry about doing Bonferroni adjustments till another video. And there's a couple other ways to do things too, but we're going to concentrate on one-way ANOVA right now, because it's a nice transition topic from first semester stats to second semester stats. So what's the farmer business got to do with it? So this is a rural province. It's kind of actually, this province is quite schizophrenic, really. No comment on that? Nobody? Nobody?
Sure.
Crickets again. Crickets no, though. You know, I grew up in southern Saskatchewan, and in the late 70s, early 80s, we had a major infestation of grasshoppers. Well, what's interesting is that crickets follow, this is a population curve, right? It's like hare and lynx, because crickets prey on grasshoppers. Grasshoppers were so thick one year, and then the following year, the crickets were so thick that you could actually skid out on the highway by running over their carcasses. I remember driving to my home. I must have been 84, I think 1984, I think it was, down this one stretch of highway. By the time I got to my parents' place, the front of my car had to have a layer of grasshopper goo, easily 3 or 4 millimeters thick, from all the smashed grasshopper carcasses. You lift the hood, they're in the air cleaner. They're in the valve train covers. It was a V6, so there's the V valley. The thing just stunk to high heaven of roasted grasshopper. I sold the car, you were still finding carcasses in there. So there's a genetics topic, you know, or populations, you know.
Mass
Anyway.
extinction event right there, bottleneck event.
Yeah, well, it is a thing. It is a thing. Mother Nature don't mess around sometimes. But where I'm going with this, although I was thinking, I just realized I could probably do that with an example here again today, but we're not going to. I want to stick to the Koopa shell thing and the Bowser topic perhaps, but the just as an explanation that I normally do, because we're in a rural province, is oftentimes when you're driving down a country road or a secondary highway like this, so this is a road and you're traveling along it, there's farmer fields off to each side. Oftentimes you see this with canola a lot, and chemical companies will work with a producer. We don't call them farmers anymore, we call them producers. And they will, so this is a road. They'll take a field like this and they'll quarter it, or cut it into strips. And they will apply a treatment of, say, a herbicide, or probably a herbicide or a fertilizer into this, and there'll be one here and one here and one here. And they'll have little signs posted so that if you're interested, you're a producer and you're an interested producer, you can see the effect on the crop growth. And this is a brilliant idea when you think about it, because just by choosing that one plot of land, think of everything you're controlling for. You're controlling for the same soil, because the chance of the soil here having a different chemical makeup from here, here, or here, not going to happen. If it rains here, it's going to rain on it all. If you get a bug infestation here, you're going to get the bugs everywhere. So you're controlling for many, many, many variables. And the only thing that's really different is what's been applied to each of these strips. And of course, there's more than two. Analysis of variance. So what you can do is you can say, well, what is the crop yield from A? It'll have an average yield. Oftentimes what they'll do, and this is for anything out in the wild too, if you want to sample, if you want to do statistical sampling of, say, what kind of life is in some meadow, you make quadrats. 1 meter square, and you get in there and you count everything. That's a quadrat. Well, obviously you're not going to do quadrats, but you can take any real size you want, and you can find the yield for each of these, and then you get a measurement. What's the yield for this? So there will be an average from here, and an average from here, and an average from each of these plots. And then you can compare them using analysis of variance techniques. Now, analysis of variance is going to tell you, are the mean values the same or not? And when you look at what we're going to do, you say, well, wait a minute, we're working with variance. Where's the mean values coming in? Well, anything that has a mean has an associated variability with it too, right? So I'm kind of getting ahead of myself here a little bit, but the idea is if the means are statistically different, then quite likely the variance is statistically different. And when we construct the analysis of variance table, I'll show you how the ratio works out. Because what we're going to be doing is we're going to compare individual averages and variances. And that's going to give us a number. Then we're going to throw away the division lines, take the whole thing, which will have a single yield, and we're going to compare the individual crop yields from each of these to the overall. And if the ratio, I'm really getting ahead of myself here, but the point is, if the ratio numbers are such that the effect of the individual treatments produces one or fewer of these things that are substantially different, you're going to get a large test statistic, because it's going to be the effect of the treatments divided by the effect of the, I'm going to use the word pooling, or the pooled data. So if this is large, usually 4 or more, we have a statistically significant number, or a statistically significant effect. So this is where we're going to end up at for one-way ANOVA. Okay, that's the idea. Now, we have to, you know what I'm going to do is I'm going to work with my agriculture example instead of Bowser.
Yeah.
You okay with
Yeah,
that? Okay. Well, I was going to do the Bowser thing, but I'm not thinking on my feet very quickly today, so let's do the Bowser thing. We'll do the Bowser thing at another time.
Yeah, I'll
we'll
prep that one and then
yeah.
we'll do it. Yeah.
Right. Okay, so what are the assumptions? Well, the assumptions for one-way analysis of variance are very much the same as the assumptions for the two-sample T comparison. Independence, don't like outliers, outliers are bad, random selection, and most importantly, the ratio. So this is step, what is it, step 0 for you?
Assumptions?
Thank you. So for step 0, we need the t-test assumptions. You know, I'm going to misspell this word to my detriment yet today. T-test assumptions. Most importantly, no outliers, and we need the ratio of the variances less than a certain value. So there's 2 ways to do this. We can either have the ratio of standard deviations. So we could have S large divided by S small. If you are given the standard deviations, this has to be less than 2. But if you're given the variances, then it's going to be S squared large divided by S squared small. This will be less than 4. Why 4? Because I'm squaring everything, right? So, depends on who's teaching you. Sometimes they use variances less than 4. Sometimes it's standard deviations less than 2. At the end of the day, it's the same thing. Have I scared everybody away yet? No?
Yeah, I'm not too sure.
Oh, we're still broadcasting, right?
Yep.
Okay, cool.
We're still on.
All right, carrying on. Now, as an example of this, let's say with our four A, B, C, and D, let's say that, let's do the standard deviations here. Okay, so this will be 7, this will be 5, this will be 6, this will be 4. So the big one is 7, the little one is 4, that's less than 2, we're golden. We can do this computation. That's the idea. So you'd either need them to give you that, them being, you know, your prof or whatever, but there's another way of doing this. More of a graphical method. And you do need to check for outliers anyway, so you should have box plots. So here we have A, B, C, and D. A, B, C, D. No, I will not do the alphabet song. Well, maybe. We'll see. So this could have a box plot that looks like this. Okay, no problem there. This could be a box plot that looks like this. Ooh, that one's not normally distributed. But if the sample size is large enough, it's all good, right? But we've got to watch out for this stuff. And over here we might have this. Okay, I'm not overly creative today, but you can clearly see that we're interested in the interquartile range. No one box is more than twice the width of another box. So this is okie dokie. This is not okie dokie. Now you get an outlier. That doesn't mean you can't do the test. It just means your results are going to be maybe not as reliable as you like. So you kind of have to eyeball it. So what does the other problem look like? Well, this one's wide. This one's, well, this is kind of stupid, but let's say it's here. Okay, so these are roughly the same. But what happens if I've got, well, that's quite a bit. Well, now you may say, I really want to break into the Talking Heads song.
Which
And
one?
you may say, where is my beautiful wife? And you may say, where is my beautiful house? No, nothing?
Not familiar with the Talking Heads.
Okay. Anyway, you could argue that this one is certainly more than twice the width of this one. So here the interquartile ranges are indicating your variability, right? And this is the center 50%, in case you forgot that. Point is, this is probably more than twice the width of this one. That's a problem. Again, reduces the reliability of your test result. Or this could have been really compact. I saw an example last semester. Someone presented for examination purposes where there was almost no whisker at the bottom. So this was highly skewed. But the point is that we're not worrying about the skew so much, but this interquartile range is certainly less than half of that. Again, that's a problem for our analysis of variance. Okay. That's my point. Step 0. Let's move on to hypotheses. These are pretty easy, actually. Whoops. Whoops. A phrase you don't want to hear when you're working at your chemistry lab fume hood and buddy next door goes, oops. You probably want to vigorously exhale and head for the door while not inhaling. Pro tip number 1. Chemistry labs with idiots are dangerous places. Boink. All right. A null hypothesis. Using my agricultural example again, we're saying that the means are statistically similar. There's no real difference. So we can say mu of field A, mu of field B, C, and D are the same. That's easy enough. You can do it in words too if you want. The alternative is, don't make this mistake. Do not do this. Mu A is not equal to mu B, is not equal to mu C, is not equal to mu D. This says one specific outcome, that they're all different. That don't work. So you don't do that. No, no, no. No. Do not do that. Don't want that. No, no, no. What we do want to say is, at least one mu, I'll use subscript I, differs from the others. Boom. Because it only takes one to be different to have a significant result. Now, how do we state significance? Well, you already know that. That's going to be the Greek letter alpha. And we're going to use 5% because I'm lazy that way. Remember, typically in first semester stats, my blue chalk's almost gone. I shift to green. So typically, we end up with 5% as default. Could be 10%, could be 1%, doesn't matter. But we could have a critical number. F crit, critical F. Critical, there we go. Now, this is a table lookup, or it's from software, one or the other, do what you want. But what's really interesting about the test statistic F is there's two measures of degrees of freedom. You need the degrees of freedom for the number of treatments, which is usually labeled up here. This will be k minus 1. We'll talk about that in detail here in a minute. And then this down here in the subscript is n minus k. So this will be a table lookup. And again, much like chi-square, the general shape of this curve is a right tail. And f crit marks the transition from the fail to reject to the reject zone. So we need to look up f crit for the appropriate percentage. And remember, if our test statistic f obtained, obtainium, lies out here, we reject the null. If it lies over here, we fail to reject the null. We'll get to that at the end of the chit chat. Okay, so that's what we're going to do. So typically f crit, depending on degrees of, or pardon me, depending on depending on these, where did I write it, these degrees of freedom. For a loose critical number, 3.5 maybe, and then you're significant, unless it's unless you got very small sample sizes. Anyway, we'll get to that. Okay, let's talk about getting the test statistic. Did I forget anything? I'm still on target, aren't I? Yeah, cool. Step 2. Now, I'm not going to do step 2 yet, so I haven't put any numbers up. But I'm going to show you how to lay out the table. I believe it was Fisher who designed this test. I think it was Fisher. I'm pretty sure it was. I can look it up later if anybody wants to tell me I'm wrong. But the idea of the table was recounted in a textbook. There's nothing really significant about the shape of the table other than it's a way to keep the computations in check, because there's a fair bit of numbers to throw around here, and it's important to know who gets divided by who. So let's do that. Let's lay out the table. So the first thing we got to have are the source of variation. Well, as we were talking earlier, we either have the data associated with assigning of treatments, or we have the data associated with taking it all together into one big collection. So we have treatments, which is sometimes called groups. This gets to be really clumsy for one reason. And I'm gonna keep rapping here through this ad anyway. Actually, maybe I'll wait. How long is this ad running? We're on 3 of 5 already. Okay, hang on here. I'm just gonna write this out. Then we have errors, which is associated with observations. So this is between, this is within, and then we have our buddy totals. There we go. We back yet? Coming. Bet we're going to get a 30-second ad right after this one. And I'm wrong. It's only 15. Okay, cool. All right. At least it's not sore bum medicine this time. It's acne cream. It's the other end. All right. Hey, we're back. Okay, cool. All right, so source of variation, just to pick it up where the ad's interrupted. We have treatments, or we can simply call them groups, and this is the measurement between groups. The observations for historical reasons that don't really make any sense are called errors, or also referred to as within groups. And then, of course, we have totals. This is highly dependent on who wrote the textbook and who's using what software. I prefer to use treatments instead of groups, but it can be either. So there's some wobble room here. Anyway, so here we have this. Let's make our table. And yes, it's a big one. Okay, so this variation is measured as sum of squares. Typically labeled SS. Sum of squares. Okay, I wrote that very badly. Let me try that again. I do have some pride. Not much, but a little bit. All right. Sum of squares. Now, we're just doing notation here, by the way. Because we really can't have a good conversation and an understanding about this entire topic unless we have the notation agreed upon. Now, let's see here. If we're using treatments, and we are, this will be labeled SSTR, treatments. If they're using groups, the notation here is typically SSG. One or the other. If we're using error, well, we always use that. This is going to be SSE. But sometimes it will be SSW. So this is treatments, which is between groups, SSG, and I've missed one. I've seen SSB in a couple of textbooks too. All means the same thing. Errors, or within groups, SSE or SSW, and this guy down here is SS, that's not an S. Oh. Boom. These just add up to that. Now, degrees of freedom come next. DF. There we are. Now, notation is one thing, computation's another. These will be computed by formulas we'll get to in a bit. I don't have room to put them all on one board. Here, this is k minus 1, where k is the number of treatments or groups. And I am going to simplify this and simply call it DFTR. Here, this is big N minus k. Now recall I said we are always subtracting the number of computed parameters. There were 4 strips in the field, which means there's going to be a group average, which is 1 parameter. There we go. Here, we're subtracting 4 parameters because each field had its own mean value. That's why this is big N minus k. We're going to call this one DFE. And this is just a bookkeeping N minus 1. We're not going to use that other than for bookkeeping in this course. We can use it for other things later. Now, here's another one of these. Depending on whose textbook and who's teaching the subject, these may be flipped around. This may be degrees of freedom, this may be sum of squares. This makes more sense for reasons you'll see momentarily. If it's the other way around, well, I'm sorry, but I wouldn't do it that way. Now, one of the things we want to know is, if I have 4 treatments, I would like to know what's the contribution of each treatment to the total variability. Well, that's just another way of saying average values, right? Of course, these are sample averages, so it's n minus 1. And that brings us to mean squares, also known as MS. So this will be MSTR. I'm not going to do the MS with these guys, so I need some room here. How do you get this? Well, that's easy. You take this, you divide it by that, and you get this. I mean, we're talking grade 5 here, people. So this divided by this gives us that. So we have SSTR divided by k minus 1. If that's not rocket science, I don't know what is. Now, what about here? Well, same thing. This is going to be MSE. And again, this divided by that gives us this. So we have SSE divided by n minus k. And that just brings us to this. This is our test statistic. big F. If there's given critical number, it'll be out here, but I don't have room. So then that means this is divided by that. MSTR, MSE, and you have your test statistics. So this is what we're going to be doing. That's the layout of the table. Now there's a couple things to know. Here I already listed K is the number of treatments. Should have mentioned that big N, not little n is associated with the treatments. Big N is total of all observations. There we go. Now there's one other little tricky thing you need to know too. What specifically is this cell here? This is the combined or pooled variance. And oftentimes you're asked for the combined or pooled standard deviation. So square root MSE comes from here. I'm just going to call it pooled standard deviation. Boom, there we go. Now, when you report the test statistic, oftentimes they say, so please tell me the test statistic under the null hypothesis, being considered under the null hypothesis. So we would say F, K minus 1, N minus K is a number, and that's how you do it. So there's the way we're going to talk about this. Now we're going to do an example. And like I said, I'm going to show you the formulas for computing this one and this one. And then I'm just going to make up some numbers, make things a little bit easier to handle here. Okay, I'm just going to step back in case anybody wants to pause the video for a moment and write that down. So this is your chance. Hit pause, and then we'll begin. Cool, okay. Let's scrub this stuff and do it the hard way. I'm even gonna wing it today. I'm feeling brave. I'm not sure if I should, but I'm feeling brave. Now, let's put the formulas over here, we'll put the computations over here. So sum of the squares of the treatments is going to be the sum of each group mean minus the grand mean, that's double bar. Square that, because otherwise we end up with 0 times n sub I. And then we have sum of the squares of the errors is going to be n minus 1 for each group times the variance for each group. And if you're familiar with the pooled t-test for 2 samples, you've already seen that. This is the connection to the pooled 2-sample t-test because this is in the pooled term, pooled denominator. Okay, now we need some numbers. A, B, C, and D. So let's see here. We need n's, we need some bars. So these will be bars, these will be squares, and these will be n's. We'll keep this nice and simple. So this is going to be 5, this is going to be 10, this is going to be 15, and this is going to be, I know you're saying, make it 20 because it's a progression. No, we're not. We're going to make it 10. Choosing numbers make this easy to do by hand, to a certain extent anyway. Now, what do we have here? Let's make you, what are we going to make you? We're going to make you an 8. And you're going to be a, no. You're going to be a 9. I think I may have just shot myself in the foot on that one. You're going to be a 6 and a 7. Remember, the ratio between these has to be less than 4, right? The big one divided by the little one, because this is variance, not standard deviation, is less than 4, we're good. Actually, I could probably made those further apart, but whatever. And we're going to have 10 observations for each of these because I simply want to demonstrate this stuff. Now, what's the grand mean? Well, the grand mean is the mean of everything. And I could wing it because the sample sizes are all the same. So what is that? That's 20, 30, 40. Oh, grand mean's going to be 10. Okay. So we're going to say double bar is 10. Again, I'm choosing that number because it makes sense. I'm doing it mentally, and this is just an example computation anyway. Because I'm not going to list all the observations because, well, we'll be here till the cows come home or my parking runs out, one or the other. We're almost done, by the way. We're at the 2/3 part. Okay. Need the sum of the squares of the treatments. That means each of these is a y, and we have to subtract the grand mean. Well, what do we get? Well, we end up with 5 minus 10 squared times 10. And then we're going to have 10 minus 10 times 10. That's 0, so that's an easy one. Here we have 15 minus 10 times 10. And again, we have 10 minus 10 times 10. So this is 0, this is 0, this is 25, 250, this one is also 250. So what do we get? The sum of the squares of the treatments is 2 times 250, so that's just 500, he said, hopefully. How am I doing? Okay, I didn't totally make a monkey of myself there. I'm running out of chalk. Luckily, I've got a drawer full. You're not getting off that easy. Okay, let's do some of the squares of the errors. You're saying, well, this isn't hard. Yeah, but if this was a data set of a couple hundred observations spread over, say, a dozen different treatments, and you're doing it by hand, you'd be there for a while. All right, so we need n minus 1. Well, n is 10 for everybody, so that's 9. And the variance is 8. Okay, so this is 72. And then well, these are all going to be 9s. And this is a 9 for 81. This is a 9 times 6 is 54. And then we have 9 times 7, which is 63. I didn't fail grade 5, unlike some people I know. Sorry, I kid. All right, what does this add up to? So 3, 4, 7, 8, 10, carry the 1, 16, 21, 270. Whoosh. Looks good? Ethan, are you going to sleep?
No.
Good, just checking.
Right.
So is that right? That makes sense? Well, these are all less than 100. Yeah, that looks about right to me. Let's just check. 3, 7, 10. Yes, carry the 1. 16, 21, 27, 270. Cool, there it is. So 270 is that. There we are. Let's make an analysis of the variance table, which we already did. We'll do it again. So here we have treatments. Here we have errors. Here we have totals. Whoosh. Sum of squares. It's a nice thing about colored chalk. You can overwrite the other ones. Okay, treatments were 500. This was 270. Adding them up, that gives us 770. We have degrees of freedom. Remember, there were 4 treatments, and that's k, so k minus 1. This is 3. We had 4 groups of 10 for 40, but 40 minus 4 is 36. This is 39, which of course makes sense. I had to find more chalk. All right. 500 divided by 3, what is that? 167 point what? 333?
500 by 3?
167.333?
167 or 166.6 repeating.
Oh, it's 2/3.
Very good. Very close.
Well, we'll just call it 167.
There you go.
160.
167, yeah.
And 2/3. Okay? 270 divided by 36, that's got to be somewhere around 80.
One more time?
270 divided by 36
Is.
yes. Was there ever a doubt? Ethan's going, he did that just like that. You know of savants? You know what idiot savant is? Guess which one I am. Okay, we need the test statistic, and as you recall from the layout of the table, the test statistic F is this number divided by this number.
Some corrections, if I may.
Yeah?
So that would be 166.67?
Oh, you're right.
Yeah. And then that 80 would actually be 7.5.
Oh.
No, sorry. Scrap the 80
Yeah?
and replace it with 7.5.
Oh, 7.5.
Yes, yeah.
Well, that makes sense.
There you
Yes.
go. Yeah. Good.
Remember, idiot savant. All right, so this number divided by this number is going to give us our test statistic F. And since I'm an idiot savant,
We are at 22.2.
22.2. This is very large,
Yeah.
so that's a statistically significant number. Hardly a surprise, I suspect. Now, this is what I was getting at when I said we're going to compare ratios. This cell represents the contribution towards the total variance attributed to the fact that we have the plots broken into 4 chunks. Each chunk contributes about that much variability. Each observation in each of the total, each observation, all 40 observations contributes this per observation. Well, actually 36, but the point I'm getting at is the variability attributed to breaking the plot of land into 4 chunks is substantially higher than the variability here or here, depending on how you want to talk about it, than just leaving it all together, which suggests to me that at least one of the plots is substantially different than the others. And this suggests that I'm right. Because if the F critical value even was a generous 5, that is much larger. So, F obtained is greater than F crit. We reject H null, which suggests at least one of the plots is substantially different than the others. Now, there's other things I can ask you. For instance, what is the combined or pooled standard deviation? It's the square root of this number. And that's got to be somewhere around 2.8. No, it's got to be
Well,
Yeah, about
2.7.
2.7.
Not too bad.
Not too bad. Well, 7.29 would be 2.7 squared.
There you go.
This is just a little bit bigger.
There you go.
So 2.7,
So now, if we
Ish.
wanted to play around with our data a little
Yeah.
bit, right? We suspect that plot D or whatever
Yeah.
was the one causing us trouble.
Yep.
And we repeated this with just A, B, C, and we got do not reject H null. We then
but
sort
there's a
of
way to determine that for the next discussion. It's called two-key honest significant difference is how to determine which plot or plots is significantly different than the others.
So Tukey is the honest way, whereas Lorenzo's is the dishonest way.
Well, no, but you're actually not far off the mark. So next time we'll explore two-key, I believe it's HSD. And that'll tell us who's who.
Who's the troublemaker?
Yep. You know, we used to do this in first semester stats, but there were so many different topics crammed into first semester statistics that we'd always run out of time at the end of the semester. and you'd have, well, okay, I got to learn this on your own, and then comes the final exam, and well, anyway, to make a longer story shorter, we can do that next time. Now, if you're going to report the test statistic, you got to have this one and this one. So it's not enough to say that just F is equal to 22.2. We want to say, I'm going to write that. We'll do it up here. F on 3 and 36 degrees of freedom is 22.2. This way, or if you don't want to do the subscript superscript, whoops, why am I doing that for? 3, 36, 22.2. Now there's no superscript, subscript. I think that's probably a lot for today, I suspect. How long have we gone on this? This has
About
got
an hour.
about an hour? Okay, that's not too bad, not too bad. Okay, so one-way analysis of variance, nothing fancy. Ooh, wobbly. We'll expand on this with Bowser shells.
Piranha plants. Piranha plants.
Oh, right, the piranha plant
Chomp,
thing.
chomp, chomp.
How many leaves, how many teeth? How many
teeth? The girthiness of the stem.
You can talk about the girthiness of the stem if you want. I'm not touching that.
On that note.
Okay, on that note, why don't we wrap it up? So we're going to look at Friday this week? How are we looking at? Or
It might be next week
Okay.
stream, yeah.
All right.
But
we're going to play it by ear, as always. I kind of miss having you up here because the otherwise I feel like I'm just doing a lecture.
Well, that's what I was going to bring up. Is now you've just signed on to do an entire lecture series on scats. So it's
Didn't I just
happening,
finish doing
and I
that?
was going to bring that up after the stream. So
Okay.
maybe we'll talk about it
All right.
now.
Okay, so let's call it a day. Thanks,
Bye,
peeps.
everybody.
Have a good one.